learn about it.
Speak smart.
Our next question comes from Dan Jones of Venice, California, who writes, I've heard a lot about air pressure and its effects, but how strong is it and why can't we feel it? Well, Dan, you are in luck, because here to prove the power of air pressure is none other than... What?
There we
Jack,
go. Okay, come on, David. Come on in here. Your team is losing. Grab
Oh,
over here.
is this my team?
Yeah, that's yours. Go ahead.
Well, thanks for letting me know.
Go
Folks,
ahead.
Jack Netlin, one of our favorite resident physicists.
Yeah, go ahead. Pull on that,
What are we
Dave.
doing, Jack?
Well, we're doing an experiment that was done about in 1600 and something, a long time ago.
pull!
Yeah. What you got here, you see, is that you got two discs right here.
Yeah?
And the air has been removed from the inside of them, and so air pressure is pushed in this way. You guys are pulling against air pressure.
So there's a vacuum inside
Well, you
there?
can say a vacuum,
And
yeah.
we're pulling against air pressure.
That's all, yeah.
Oh, but we're not getting anywhere.
Well, in fact, if I were to let the air back in, watch what happens here. Yeah, there it goes. Well, that was pretty easy.
Yeah, good, Jack.
Okay, you guys, take 5. Oh, boy, that's quite a thing, huh?
Yeah, what a way to start, Jack.
Yeah.
What exactly was going on with these discs again?
Well, I had removed the air from the space between these two discs. And in so doing, I created a vacuum in here, and so the air pressure on the outside was pushing them together. And then I opened the valve back up, let the air back in.
And we know what happened when you did that.
Yeah, you guys looked kind of silly there for a second. So, and, you know, I can do that same kind of thing. I could make a vacuum with the straw, and I could get some of this punch up the straw.
And get a drink.
Okay, it tastes kind of good, yeah.
Good, Jack. Can I have a drink? I'm kind of thirsty
Well,
after the tug of war.
So actually, this is yours over here, David. Why don't you step right inside here, and we can have you...
drink the one on the floor, huh?
Sure, yeah. We can have you go on up there and drink through a long straw.
What is it, a 15-foot
Go ahead,
long
keep
straw?
on going, yeah. Push the button, and up you'll go. And
Ooh, look at this. There's
stretch it
no
out.
way, Jack.
Sure, that's good. Now, go ahead and pull on that like you always would a straw, and we'll notice the liquid in fact starting to come up here. As you're reducing the pressure inside the tube, the liquid comes on up because the air pressure outside is pushing downward on the top of the liquid. There it is, coming up there, Dave. Yeah, you're getting there now. There, you got some liquid.
Ah, that's a lot of work for a refreshing drink.
Yeah, it sure is.
I can't believe I was able to get a drink out of a 15-foot straw.
Sure you can. If you use the weight of the atmosphere like that, it'll do that for you.
Now, Jack, you keep talking about the weight of the atmosphere.
Yeah.
And we've got atmosphere in the studio here, right?
Sure do.
So I don't feel a lot of weight.
Well, no, you don't. But that's because the weight of the atmosphere is compensated for by the pressure from the inside of your body pushing back out again.
The air and the fluids in my body.
You bet.
Pushing out.
So the net result is nothing.
All right, now how much pressure are we talking about, Jack?
Well, we're talking about quite a bit because you see there's about a 50-mile ocean of air we're under here, and so it pushes down with a whole lot of pressure. In fact, I've got an illustration that will show you the pressure right back over here. You notice I have here a sack of potatoes. Grab a hold of those, David. Yeah. That's
how much is that?
15
pounds of
You
potatoes.
bet. That's about close to 14.7 pounds, which is atmospheric pressure, 14.7 pounds per square inch. Now, if you take this rod right here, it weighs 14.7 pounds.
That's heavy.
And it's 1 square inch of area, and so that's how much pressure is pushing on 1 square inch of area of everything that we have.
So this is the column, in a sense, of pressure that was pushing down on the juice, forcing the liquid up in my 15-foot straw.
That's exactly right. And in fact, if you were strong enough, you would be able to pull it up about 32 feet, or push it up about 32 feet if it were water like...
Not me. I was pushing it at 15.
Yeah, it's very difficult. Now, it isn't practical to use water for that purpose. And so what we do is we measure barometric pressure with a barometer like this. This is a mercury barometer. And the liquid we use is much, much denser than water.
This is liquid mercury here, basically.
The column that it will hold is much, much shorter. See, right there now, if I raise it any higher than that, it just stays right there. Even though the tube goes up or down, it stays at that height because that's how much mercury can be supported by 14.7 pounds per square inch.
Pushing down on the fluid here.
That's right. And so now you hear the weather reports and they say the barometric pressure today is 29.2 inches of mercury and rising. Or whatever.
I always get confused on that. When the barometric pressure is rising, is that good news, good weather?
Yeah, that's good weather.
Okay.
And when it's lowering, then it's bad weather. And so they make these maps that show where the high pressure systems are and the low pressure and so on. And actually, it's the difference in those pressures that give us some idea of the effect of barometric pressure.
Okay.
And I've got another thing I'll show you now that really shows the effect of a difference in pressure. Come on over here. Okay, David, what we're going to do here is we're going to create a tremendous difference in pressure. If you'll turn the fire off